We can assign oxidation states or oxidation numbers to atoms in a reaction, and by following the change in that oxidation number for an element, we can deduce whether it's been oxidized or reduced during a reaction. We can also use the idea of oxidation states to write half equations for more complicated examples. But first of all, we need to be clear on the rules for assigning oxidation states, and they're fairly straightforward. Rule number 1, the oxidation state of atoms in an element is 0. So, for example, if I have a reaction that involves sodium or maybe bromine, because they are present in this reaction as elements, their oxidation state is 0. And we're assigning an oxidation state for the atom in that element, molecule, compound. That will become clearer in a second. Rule number 2. For simple ions, the oxidation state is the charge on the ion. So, for example, if I take a bromide ion, its charge is -1. So it has an oxidation state of -1. And we need to be very clear here that we write the charge goes in front of the number. Okay, another example. Oxide ion. It would have an oxidation state of -2. Magnesium, another simple ion, it's got a 2+ charge. It would have an oxidation state of +2. So we might say, for example, the oxidation state of magnesium in magnesium chloride is +2 because that is the charge on the magnesium ion. Rule number 3. In an uncharged compound, the sum of the oxidation states is 0. I'd like to look at a couple of examples. I'd like to look at carbon dioxide and ammonia. But before I do so, we also need to be aware that there are some elements whose oxidation state rarely changes regardless of whoever they're in a compound with. First one is oxygen. Oxygen nearly always has an oxidation state of -2. And hydrogen nearly always has an oxidation state of +1. I'm going to come on to a couple of exceptions towards the end of this video. The third one is fluorine, which does always have an oxidation state of -1, regardless of what it is bonded to. So this is our starting point. If I go back to carbon dioxide, I know that the oxidation state of oxygen is going to be -2. There are 2 atoms of oxygen, each with an oxidation state of -2. So carbon must have an oxidation state of +4. Once again, remember that the sign goes in front of the number, and we are quoting the oxidation state per atom. So we need to be really clear that when we say oxygen here has an oxidation state of -2, it does not have an oxidation state of -4. The fact that there are 2 of them is relevant for assigning an oxidation state to the carbon. Similarly, if I look at hydrogen, hydrogen in ammonia has an oxidation state of +1. There are 3 of them, which means that nitrogen must have an oxidation state of -3. Rule number 4. For polyatomic ions, the sum of the oxidation states equals the charge on the ion. So a polyatomic ion is one that has more than one element in it. I'm thinking something like sulfate ion. If I would like to assign oxidation states to the atoms in this ion, I know that oxygen has an oxidation state of -2. There are 4 of them. 4 lots of -2 is -8, which means that the oxidation state of sulfur must be +6, because +6 minus 8 is -2, i.e. the sum of those oxidation numbers, oxidation states, equals the charge on the ion. If I were to take maybe a different sulfate ion, SO3, 2-, then once again the oxidation state of oxygen here is -2. There are 3 of them. So the oxidation state of sulfur in this sulfate ion must be +4. +4 minus 6 comes to -2, which is the charge on the ion. We can, in modern times, we can again put the oxidation state into the name. So this would be sulfate 6 ion, and this one here would be sulfate 4 ion, as in copper sulfate 6 or copper sulfate 4, for example. The number here refers to the oxidation state of the sulfur in this ion, and ATE means that we've got oxygen present. It's an oxyanion, which is a term that you may come across. Let's have a look at a couple more complex examples. This is a common oxidizing agent, KMnO4. How do we assign the oxidation states here? Well, there are some things that we're just expected to know at A level. Firstly, the potassium is in group 1. It's a simple ion. I know that it exists as K+, so its oxidation state is going to be +1. That in itself tells me that the manganate ion must have a charge of -1. Some of these will become really familiar because we're going to come across them a huge amount at A level. But at the moment, we can use these basic rules to pull it apart. Now that I know that that has a charge of -1, I know that oxygen has an oxidation state of -2. There are 4 of them. So the manganese must have an oxidation state of +7, because +7 minus 8 is -1, which is the charge on that particular ion. And overall, this compound is neutral, and that works as well in terms of the oxidation states there. How would I name this? I would name it potassium manganate 7. Whereas the 7 here refers to the oxidation state of manganese in the manganate ion. Na2Cr2O7. So once again, we need to appreciate that I've got 2 ions in this compound. Sodium, group 1, it's a simple ion, so its oxidation state is going to be +1, which means that this Cr2O7, this chromate ion, has an overall charge of -2. Oxygen, we can see, has got the oxidation state of -2, and there are 7 of them. 3, 4, 5, 6, 7. So altogether that comes to -14, which means that each of the chromiums must have an oxidation state of +6, because +6 plus 6 is 12, 12 minus 14 is -2, and that is the charge on the ion. Again, be really clear here that we are quoting the oxidation state for the atom, each atom in our compound or in our ion. So we would say that chromium has an oxidation state of +6. We don't say that chromium has an oxidation state of +12. Now, the fact that the oxidation state of atoms changes depending on the compound that it's in, or whether it's an element, has an effect on its name for some compounds. I'm thinking particularly of the transition metals, where multiple oxidation state is a key property of these elements. So let's take copper oxide, CuO. Oxygen has an oxidation state of -2. Copper has an oxidation state of +2. I would name this copper 2 oxide. Not to be confused with copper 1 oxide. Copper 1 oxide has the formula Cu2O. Oxygen, again, has the oxidation state of -2. Copper here must have an oxidation state of +1 because there are 2 of them. Remember that the oxidation states in a neutral compound equals 0. Name of this, copper 1 oxide. Now, I've been quite careful here in the way that I've written it. First of all, the oxidation state is in Roman numerals, bracketed, and there is no gap between that and the name. So copper 2, copper 1, this should all look like it's one word when you write it, then gap, then oxide. So let's have a look at some of the exceptions and unusual cases, the ones that get thrown up quite a lot. First one, oxygen bonded to fluorine. Well, usually we would say that oxygen has an oxidation state of -2, and we know that fluorine is always -1, so clearly that doesn't work. This is a system that is based originally on the electronegativity of different elements. Fluorine is more electronegative than oxygen, so fluorine is always going to be -1. There are two of them, so when oxygen is bonded to fluorine, its oxidation state is not necessarily -2. In this case, it's +2. Second unusual case, you should be aware of the oxyanions of chlorine, but it also goes for bromine and iodine. There are lots of them. ClO-. In this case, oxygen is always -2, so chlorine has got to be +1. This is the chlorate 1 ion. But we've also got the chlorate 3 ion. We have got the chlorate 5 ion and the chlorate 7 ion. And once again, the 3, the 5, the 7 refer to the oxidation state of chlorine in each of these ions. We see a similar thing with bromine, bromate 1, bromate 3, bromate 5, and with iodine, iodate. Third unusual case involves hydrogen. In the case of metal hydrides, so I'm thinking of something like lithium hydride. In the metal hydrides, lithium is +1, so hydrogen is -1. So we're saying that hydrogen always has an oxidation state of +1 in its compounds, except in the metal hydrides, where it's going to have an oxidation state of -1. And finally, a couple of weird oxides that you might come across. Superoxide and the peroxide ion. So the superoxide ion, for example, you might see it in potassium superoxide, so KO2. Potassium has an oxidation state of +1, and oxygen has an oxidation state of -0.5. What does a superoxide ion look like? Well, we have a single bond between the two oxygens. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and then it's got a single negative charge, so it's picked up an electron from the potassium in this case, and it looks like so. So one of the oxygens has 7 electrons around it, the other one has 8. An example of a peroxide, hydrogen peroxide, for example. What does this look like? Well, we have the oxygen. Again, there is a single bond between the oxygens. And if hydrogen has an oxidation state of +1, then each of the oxygens has an oxidation state of -1. So just to be aware of those two examples. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the description below, it'll take you straight to Crunch Chemistry School, where you can access my free maths skills course, complete tuition, and worksheets designed specifically to build your confidence and stretch you. Together we can do this.